The rotor buggy does not begin as a joke, although it will later be treated as one. It begins as a logistics problem, written in staff college language, circulated in memoranda between the War Office and the Airborne Forces experimental establishment. By late 1942, British airborne doctrine is constrained by mass. Gliders can land men. They can land light artillery. They cannot reliably land a standard utility vehicle without consuming an entire airframe. The Willys MB Jeep has already proven itself indispensable. It moves officers, radios, ammunition, and wounded. It is small but not small enough. A Horsa glider can carry one, but doing so displaces troops. A Hamilcar can carry more, but Hamilcars are scarce and prioritised for tanks. The question becomes administrative before it becomes technical. How to land a Jeep without using a glider? Raoul Hafner is already known to the British establishment. An Austrian émigré, a rotorcraft specialist, a man who believes that autorotation is not an exotic phenomenon, but a practical solution. His work on autogyros has attracted attention because it sits between categories. Not a helicopter, not an airplane, something that descends rather than climbs. Hafner's proposal is framed carefully. No engine, no powered flight, no pilot in the conventional sense. The Jeep will be towed aloft behind a transport aircraft. At release, it will descend under a free-spinning rotor, landing on its own wheels. The Jeep will drive away. No glider recovery, no wrecked airframe, no additional crew. On paper, this satisfies several departments simultaneously. The Air Ministry sees no new powered aircraft. The War Office sees a vehicle delivered intact. The Treasury sees minimal new materials. The danger is conceptual rather than obvious. The Jeep is not designed to fly. Its frontal area is large. Its mass distribution is poor. Its suspension is compliant. Its steering geometry is not meant to transmit aerodynamic loads. These objections are noted. They are not decisive. Wartime Britain does not reject ideas for being strange. It rejects them for failing tests. The Hafner rotor buggy is formally designated the Malcolm rotorplane in some documents, but the name does not stick. The workshop nickname does. Rotor buggy, a Jeep with a rotor mast bolted through its chassis, a tail assembly attached to the rear bumper and frame rails. The rotor itself is a two-bladed wooden structure, approximately 40 feet in diameter, derived from Hafner's earlier autogyro work. It is not light. It is not rigid in the way a fixed wing is rigid. It flaps. It teeters. It must be controlled. Control is the central compromise. There is no separate cockpit. The driver's seat remains the seat. The steering wheel remains the primary interface. Through a series of linkages, rods and bell cranks, the Jeep's steering wheel is connected to the rotor head. Turning the wheel tilts the rotor disc. This is conceptually elegant and mechanically alarming. Automotive steering systems are designed for lateral loads transmitted through rubber tyres at low speed. Here, the same wheel is asked to manage pitch and roll moments generated by a rotor disc, encountering turbulent air at towing speeds exceeding 100 miles per hour. The tail is added to provide directional stability. It consists of a tubular framework covered in fabric with a vertical fin and horizontal stabilizers. It is bolted on. It is braced with wires. It is designed to be jettisoned after landing. The Jeep's rear axle is not designed to carry aerodynamic lift loads. Reinforcements are added. Plates are welded. Weight increases. Every reinforcement solves one problem and worsens another. Towing tests begin cautiously. The rotor buggy is towed behind a truck on an airfield to test rotor spin-up. The rotor does spin, autorotation occurs. The mast vibrates. The steering wheel moves in the driver's hands without input. This is recorded without comment. The next phase involves towing behind an aircraft on the ground. The Jeep lifts slightly. The suspension unloads unevenly. One wheel leaves the ground before the others. This asymmetry is noted in test reports as undesirable but manageable. The first airborne tow is conducted behind a bomber, not because it is ideal, but because it is available. The tow rope is long. The release mechanism is simple. The pilot of the Jeep is not a trained aviator. He is a test driver with brief instruction. There is no dual control. There is no instructor. The aircraft accelerates. The rotor spins faster. The Jeep lifts. It does not lift cleanly. It oscillates. The rotor disc hunts for equilibrium. The tail provides some damping, but not enough. In flight, the rotor buggy behaves exactly as its shape suggests. It is aerodynamically inefficient. The Jeep body produces drag. The exposed wheels produce drag. The windshield frame produces drag. The rotor must generate lift while overcoming this drag without the benefit of forward thrust. The tow aircraft must fly faster than optimal to maintain altitude. This increases loads on the tow rope. The pilot in the Jeep experiences constant vibration. The steering wheel requires continuous correction. There is no trim, there is only effort. Reports describe the experience in understated language. Control force is heavy, response delayed, considerable physical exertion required. The rotor flaps in turbulence. Each flap transmits through the mast into the chassis. The chassis flexes, the steering column flexes. The driver's hands are not isolated from these forces. There is no power assistance. The wheel kicks. The driver braces his feet against the floor. Release tests are more concerning. When the tow rope is released, the Jeep transitions from a towed state to a free descent. The rotor must immediately assume full load. In several tests, this transition is abrupt. The nose pitches down, the driver hauls back on the wheel. The rotor disc lags, then overcorrects. Oscillation follows. The descent rate stabilizes eventually, but not smoothly. Landing is survivable, but not precise. The Jeep touches down hard. The suspension absorbs some energy. The rotor continues spinning overhead. There is a brief period where the vehicle is neither fully flying nor fully driving. The landing sequence requires the pilot to stop the rotor. There is a brake. It is mechanical. It is marginal. In some tests, the rotor continues to turn as the Jeep begins to roll forward. This creates additional hazards. The tail assembly must be jettisoned. This requires a manual action. Under stress, sequence errors occur. These are noted. Procedures are rewritten. Parallel to flight testing, administrative correspondence accumulates. The airborne forces ask about training requirements. The answer is unclear. Is the driver a pilot? Is he a driver? Is he both? The Air Ministry raises certification questions. The rotor buggy is not an aircraft. It is not a glider. It is not a vehicle. It occupies an administrative void. This slows progress more than any single technical flaw. Manufacturing considerations are examined. Each rotor buggy requires a standard Jeep plus a rotor assembly and tail. The rotor blades require skilled woodworking. The tail requires fabric and tubing. None of this is impossible. None of it is free. Gliders, by contrast, are already in production. They carry multiple loads. The cost-benefit analysis begins to shift. Further tests do not improve confidence. Stability remains marginal. Control remains exhausting. Towing aircraft crews report difficulty maintaining formation. The rotor buggy does not track smoothly behind the tug. In turbulence, it yaws. The tow rope transmits these motions back to the aircraft. This is undesirable. No one wants a Jeep influencing a bomber's flight path. By late 1943, attention has moved elsewhere. Larger gliders are coming online. Airborne doctrine is evolving. The need to land a single Jeep without a glider is less acute. The rotor buggy is not formally cancelled in a dramatic sense. It is simply not pursued. Reports are filed. Hardware is stored. Hafner moves on to other projects, including work that will eventually contribute to practical helicopters. The rotor buggy survives in photographs and test reports. It is often described as absurd. This is inaccurate. It is rational within its constraints. It applies known aerodynamic principles to a new problem. It fails not because it violates physics, but because it obeys them too strictly. A Jeep is heavy. It is blunt. It is not meant to fly. Autorotation can compensate only so much. The most revealing aspect of the rotor buggy is not its appearance, but its control philosophy. The decision to use a steering wheel to control a rotor disc reflects a wartime willingness to blur boundaries. Automotive controls are repurposed for flight. The human operator becomes the flexible element compensating for mismatched systems. This is efficient on paper, is punishing in practice. In the end, the rotor buggy demonstrates the limits of improvisation. It also demonstrates the breadth of experimentation tolerated under wartime pressure. No one is punished for proposing it. No one is celebrated for abandoning it. It simply exists, briefly, as a solution that was tested and found wanting. The test documentation does not stop when flight testing slows. It becomes denser. As the prospect of operational deployment recedes, the paperwork expands rather than contracts. Engineering sections are asked to justify earlier assumptions. Weight tables are revised repeatedly, the base Willys MB chassis mass is listed, then amended to include reinforcements. The mast assembly weight is recalculated after cracks are found in early fittings. Each added gusset is measured. Each bolt is specified. The cumulative effect is predictable. The empty weight increases beyond the margins originally assumed by Hafner's rotor calculations. Autorotation performance degrades incrementally, not catastrophically, but enough to matter. One memorandum addresses vibration transmission. Accelerometers are mounted temporarily to the chassis rails. Data is crude by modern standards. Needle deflection recorded on smoked paper. The conclusion is cautious. Resonant frequencies overlap between the rotor system and the Jeep's suspension. This creates amplification rather than damping. Rubber bushings are proposed. They are rejected because they introduce compliance where rigidity is required. Metal-to-metal joints remain. The vibration remains. Another report focuses on steering loads. Torque values at the steering wheel rim are measured during tow. The numbers are high, higher than those encountered in ground operation. Sustained loads are the issue, not peak loads. A driver can tolerate a brief shock. He cannot maintain constant force for extended periods without fatigue. Fatigue leads to overcorrection. Overcorrection leads to oscillation. Oscillation leads to loss of control margin. This chain is noted explicitly. There is discussion of alternative control schemes. A separate control column is sketched. Foot pedals are considered. These are rejected because they complicate training and modify the Jeep beyond easy reversion to ground use. One of the selling points of the rotor buggy is that it can be returned to a normal vehicle quickly. Every additional control undermines that claim. The design is trapped by its own premise. Logistical officers raise questions about recovery. A landed rotor buggy still carries a rotor mast and blades overhead. Removing them in the field requires tools and time. The blades are long. They are fragile. Transporting them after landing negates some of the logistical advantage. If they are abandoned, they represent wasted material. No satisfactory field procedure is developed. Safety officers contribute understated notes. One mentions the risk of rotor strike during uneven landings. Another notes that in a crosswind, the rotor disc may tilt sufficiently to contact the ground before full weight is on the wheels. This scenario is not tested deliberately. It is acknowledged and avoided. Correspondence with airborne units reveals skepticism. Infantry officers are unconvinced that delivering a single Jeep justifies the complexity. They prefer additional men or heavier weapons. The Jeep is useful but not decisive. In an airborne landing, priorities are compressed. Every risk must justify itself. The rotor buggy struggles to do so. There is also the matter of towing aircraft availability. Each rotor buggy occupies a tow aircraft for the duration of flight. That aircraft cannot tow a glider simultaneously. The operational arithmetic is unfavourable. One aircraft, one Jeep, versus one aircraft, one glider. Dozens of men. This comparison appears repeatedly in marginal notes. Hafner defends his work professionally. He does not claim perfection. He argues that refinement will improve stability. He suggests better rotor profiles. He suggests incremental changes. The committees acknowledge this. They also note time constraints. Refinement requires testing. Testing requires resources. Resources are finite. By earlier footfall, attention has shifted decisively to established systems. The rotor buggy remains officially extant but practically dormant. It is not destroyed. It is stored. Photographs are taken. Measurements are archived. The project fades without a formal termination order. In later evaluations, the rotor buggy is sometimes described as an example of eccentric British engineering. This interpretation misses the administrative reality. It is an example of a system pushed to its logical extreme. If gliders are scarce, make the load into the glider. If pilots are scarce, make the driver into the pilot. If engines are complex, remove the engine. Each step is logical. The accumulation is not. The rotor buggy's legacy is indirect. Hafner's understanding of rotor behaviour under adverse loading contributes to later rotor craft development. The data on autorotation with high-drag fuselages informs future designs by showing what not to do. The project serves as a boundary marker. Beyond this point, the compromises outweigh the gains. The Jeep itself returns to its intended role. It is loaded into gliders. It is driven off ramps. It breaks axles. It is repaired. It does not fly again. The rotor blades are repurposed or discarded. The tail frameworks rust quietly. What remains is the paper trail, memos, test sheets, diagrams, a steering wheel connected to a rotor head drawn carefully in ink. It is a reminder that wartime innovation is not a straight line towards success. It is a field of explored dead ends, mapped in detail, and then left behind.